Hello, Twitch fam. Getting started a little early tonight just to see how everybody's doing. And we'll get going soon. Tonight is just coding. I don't have any actual slides or anything to share. We're going to code almost the entire time. I'm sure you're going to have a lot of questions, so I'm going to facilitate those questions and see how we do. And I guess before we get started, I'll just wait till some people log on, but I'm happy to take any questions that you have as we go. Certainly pause me if I get too far ahead. I'm happy to answer any questions. Also, so I can help people with pre-roll, I'm going to go ahead and run a 60-second ad break and get one of those out of the way. How about that? And I don't know what that looks like on your end, but I hope everything's good. Oh, I bet because I didn't sign in to see my own Twitch stream that I don't get to see the ad. Hello, Twitch fam. How's everything going today? We'll get started soon. I just hopped on a little early so I could answer questions for folks if they had any. I'm going to post the link to the first notebook very soon. So sit back, grab some water. We'll get going real soon. Yep, tonight's almost all coding, so I won't have a classic presentation or short lecture to give. We'll just dive right into the data tonight. I do plan on starting right at 7, so we've got about 3 minutes, and I'll post the link shortly to the notebook so that everybody has access. All right, let's send that link out for you. All right, I just posted the link to the notebook in chat. So if you go ahead and click that, and then when you do click that link, there's another one you need to hit. Hit open in Colab. That way the code opens. You can actually execute the code in the cells. All right, so we'll get going shortly. All right, welcome to Twitch tutorial part 3. Tonight we're going to go through the data. I don't have a presentation to give. We're just going to dive right into the code. So if you're following along, I'll post the link one more time in Twitch chat. If you'll open that link and then click open in Colab, we'll get going. And I'll make sure that once this gets posted to YouTube that these links are available for you. So when you open that link and then click open in Colab, you'll see the same notebook that I'm looking at. I just have set it up in dark view. So if you go to tools and then go to settings, you can change it from light to dark. So light or dark. I prefer the dark view. A little easier on the eyes if you're coding all day, which some of us do. Previously in the notebooks I was using, I was only downloading 50,000 rows. This time I'm using all of the data. All of the data is, well, it's a long download first off. Secondly, it uses a lot of RAM. So do be careful if you're running these notebooks locally that you don't exceed the resources of your machine. I have not encountered problems with this when I tested it in Google Colab, so you should be fine. Also, since the notebook's been run before, a lot of the outputs pre-computed, so you don't necessarily have to run the code, although you might as well. That way you get the benefit of running it yourself. So let's go ahead and get started. What I'll need you to do is just run this cell, and you'll see that it takes a little bit of time. But do note, there's 2 links that I'm storing here. I'm storing the link to the training data inside the variable training data path, and the tournament data is stored in tournament data path. I'm creating 2 new data frames using pandas, and I'm storing them in df_train and df_tournament. And this is consistent with what we did in the previous notebooks, so this should look familiar to you. And you'll note that the download takes a bit of time. That's to be expected. All right. Anybody have questions in Twitch while waiting on the data to download? It's a great chance to let me know if you have any concerns or comments. I want to also thank you for pushing me over the edge for affiliate status. I really appreciate that. We have more emojis to use in the Twitch chat. Also, the ability to subscribe. I'm still trying to figure out what features I want to add for subscribers, but I imagine they will be coding related. Perhaps some custom content for subscribers. But I'll develop that as time goes on. For now, I'm happy to share it with everybody. Now, once this loads, it will go pretty quick. There aren't too many cells that take this long to load. And you can tell that it's still loading by the status here, where my mouse is. When the circle is running, it does indicate that the cell is processing. So how's it going tonight, Twitch fam? Everybody good? All right, that finished. So most of this code is taken from the Numerai example script page. And what I did is I copied over code that I thought was important to notice and to kind of go over the data. So this cell, what we're trying to do, and it's pre-calculated in case you don't want to run it, is just merely to show the number of columns per feature group. There's 6 feature groups. And if you're a RPG fan, you may notice that some of these have familiar names, right? Charisma has 86 columns, Constitution 114, Dexterity has 14 columns, Intelligence has 12, Strength 38, Wisdom 46. We have no idea what these mean. The data is obfuscated, and Numerai purposely does not tell us what the data represents. But they're at least telling us that these features are grouped together. So let's take a look at that. What does that mean that they're grouped together? Well, let's take a look at it, right? So this code is pre-written, but we're going to import matplotlib as PLT. We're going to use Seaborn as SNS. We're going to use that style so that we can see it. We're counting the number of eras, and we're counting it and plotting it. We're looking at observations by era. Okay, so let's run this. You can see there are 120 eras. The average era has 4,181 rows. The standard deviation is 583. The minimum number of rows is 2,371. And you can see the percentile ranks. The max is 4,893 rows. But we can graph that representation. So you see in the early part of the era sets, there are fewer observations and it climbs over time. There's a dip in the data. Not sure why. It's never been directly exposed as to what it means that there's a dip in the number of observations. But if you think of equities, we can kind of infer that there are just fewer stocks that are present in the training data between, well, approximately era 55 and 70. Something happens where the number of stocks declines and then it rises again toward the end. There are 120 eras. An era represents 1 month of trading data. We're predicting 1 month from now. So we take today's known equity position and try to predict what happens in the future. Okay, so that's what we're looking at here. Now, we created that convenience function to capture the features. Let's look at it. So let's describe each feature. This may take a second for it to process. If you are doing this locally, please let me know and see if the runtimes are similar. I'm curious. But if you wanted to look, there are descriptive statistics for each of the 310 feature columns, and the name is at the top. So for all of the rows on feature intelligence 1, you can see the mean, the standard, and the min. We looked at this briefly in the subset of data, but now that we have all 500,000 plus rows, you can see that that holds true throughout the entire sample. That's very interesting. So I'm not going to look at all of them, but you can just scroll across and you can see that that's consistent. It's very interesting. Okay, I'll try not to scroll too fast so I don't get you seasick. But that's how we would look at the era distributions and descriptive statistics of it. Now, we do have a target column, right? Because we have a dependent variable. We also went through that in a previous session. Now, I pre-ran it, so if you don't want to, you don't have to, but I'm going to run it now. I'm going to store the target, okay, the target column, which can be accessed in such a way here. This is pre-written for you. And then we're going to describe it. So we take dftrain target and describe it, okay? And you'll see, again, 501,808 rows. The average is 0.5. And again, even the target across the entire data set still has this interesting distribution. So let's look at the number of observations per target value. So here again, we're taking the train data set on the target, and We're applying a lambda function in pandas. So the lambda function is the value counts of x for the target. So for each value of the target, we get some interesting statistics. Note that they're pretty evenly distributed. They would kind of have to be for the descriptive statistics to represent what they do. It's approximately 100,000 targets per target value. And here we can plot that relationship. So this is pre-written for you just to plot the distribution of the targets. And so you can see quite clearly how they're extremely even. And at the midpoint, there's just a couple of more. Either way, that matches quite clearly what we have here. All right. This is pretty important because the training data takes a lot of space. Okay. Before I run this cell, if I run this first, dftrain.info, it shows that the memory usage is 1.2 gigabytes. If you look in Colab here, you can see how much resources are being used. The RAM is just a status bar. Okay, but if you hover over, it'll show you that there are 7.5 gigabytes of 12.7 gigabytes being used and 30 gigs of space stored out of 107 available. So we're within the limits of what we need, but we can do better. That's what it's all about, right? So what we have here is a function that reduces the size of the memory usage by converting the features to the float16 data type. Let's do that. Let's let that process. So what it's doing is it's taking it from float64 and converting it to float16. It will not decrease the performance of the algorithm because we don't need that much precision anyway. As you saw, the feature columns have 5 discrete values anyway, and that's true also for the target. So we can reduce the amount of memory used. We'll also want to do this for the tournament data, but wait until I show you how much resources the tournament data uses. It's very, very high. So if you're just logging on, I put the link in chats for this notebook. I'll just post it one more time so that you can catch up. If you're going to run this code locally, let me know because it's going to take you a little bit of time to get it set up. But everything works. I ran this ahead of time to make sure that everything works for you. And if you click that link, just click open in Colab or leave the code in place and just scroll along because I'm going to run the code here on the Twitch stream so you don't have to. Okay, so that completed. We went from 1.2 gigabytes to what? Let's take a look. 309. So we had a very large reduction in memory usage. Now let's take a look at the tournament info. Now, because I ran that before, is 3.8 gigabytes of space. Yikes. 3.8 gigabytes of memory usage, and it shows you that the test data includes 1.5 million rows. Validation by itself is a little over 100,000. And the live data, this is what we're sending predictions on. This is what we're building all this modeling for, is to predict on 5,170 individual stocks and to provide the hedge fund with a ranking of what we think the number one pick and the last pick are for our model. That's the objective. And you'll see that for the data type, it's int64. We don't need that. Also, we don't need float64. So let's do this again. Let's run this one and reduce the size. So we went from 3.8 gigs of RAM. We're going to cut that down a lot. We're going to reduce it to 1 gig of RAM. But let's let that finish, and I'll show you how that works. We've got a lot of coding to do tonight because I'm going to take you all the way up to building a production model. That's right. So I'm going to show you how to optimize your model on the training data and then how to ensemble it together, and I'll show you why that's important. And at the very end, you're going to be able to generate predictions that you can submit to Numerai yourself. And we will have done it in 3 nights. I think it'll be a total of just less than 5 hours of tutorials. We went from knowing nothing to having example code that we can modify and build a complete production model on. Also, some of this is programmatic with an API. And so if you set this up correctly on Sundays, we'll just say Sundays because that's the safest day that the tournament data refreshes. But on Sundays, you can just open this notebook. Well, not this particular notebook, but your production notebook, and click Run All, and it will update your model and upload the predictions to the hedge fund with no further action on your part. Once you've decided on the structure of your tournament model, that's it. That's all you have to do. And then you can clone these notebooks and come up with even more ideas and deploy those. Since the hedge fund allows 10 models per account, it gives you a chance to create 10 separate unique models. Now, what the code is doing in the background is it's going through and it's converting the data type for each feature column in the tournament data set and reducing the memory size. So we're going to go from 3.8 gigabytes of RAM all the way down to just over 1 gig. That's a huge amount of savings of memory. And it could be important if you have an older laptop or if you're having trouble with run times. This could potentially save you some headache. There are even more ways to do this. And I think when I start the advanced series of tutorials, we'll get into that too. This is merely scratching the surface, but I think you'll find that this will give you a great leg up on the tournament. Any questions so far? Well, thanks for hopping on anyway. At any point during the stream you do have questions, please go ahead and send a message in chat. Also, I will have to run some ads because now I'm an affiliate. And so to prevent the pre-roll ad, which is like the ad you have to see if you log on, I want to prevent that. So I'm going to periodically have to run a 1-minute ad every now and then, approximately every 20 minutes. So I think in 5 minutes I'll run the next ad. And if you subscribe, there are no ads, so that's a benefit as well. All right, so that finished. Let's just double check, right? So there it is, less than 1 gig of RAM, or a little over 1 gig of RAM used, but we saved almost 4 gigs of RAM by doing that. Let's take a look at the tournament data. Let's just look at the first 5 rows, right? So it starts with era 121. So this is our out of sample. This is the most important part, basically, of all the tutorials, is looking at out of sample data, because we need our models to be trained on data that is in fact truly unseen. And that's what the hedge fund gives us. They give us a set of validation data. It consists of 22 eras. So the distribution is very similar, so the format's the same. So let's take the era numbers and slice it out. So we only want to keep the ones with eras. Okay, so we're going to take the era numbers for the train set and capture the target. Additionally, Numerai provides us the correlation functions. So the actual Numerai score is your rank correlation, your Spearman's R. But we can use Pearson correlation as a proxy. But the difference between the two is minimal, and it quite honestly runs faster. So it's fine just to use that. So what we do is we create these functions and we store them. So let's take a look at the feature correlations, right? Because you should know that some of these features are highly correlated with each other, right? So let's create a new variable and store the features correlations in this new variable, and then let's put it in a format that we can read. So that's what this next step does. And since it's pre-printed, we'll just look at the first 5, and you can see that they have some correlation, but look at intelligence 4 is highly correlated with intelligence 1, 65%. So it isn't true for all of them, but it's true for some of them, and that becomes problematic. So in the last tutorial, I said that try to identify models that deal with multicollinearity, and that's why I said that, because some of the feature columns are highly correlated with each other, and that can cause problems. It can lead to overfitting of your model and could potentially bias the estimates that it makes. Also, this is coming from, hold on, let me just find this link, because I want to show you the genesis of this came from two places. One is here. The other is here. I took two notebooks and I blended them together for our purposes tonight. All right, so that one ran. Let's take a look at this one more time. As you can see, intelligence 1 and intelligence 4 are highly correlated. Some of them are not so much. But I believe it is important to pick models that deal with multicollinearity or do something else to help prevent them from overwhelming the model. So let's just look at the highest correlated one. So you'll see that they run in groups. Constitution is correlated with each other. So 112 with Constitution 9, 33 with 46, and down the line also you'll see in terms of the sorts, it kind of looks at the top, well, in this case, negatives and positives. You can see that wisdom and wisdom are tied up in Constitution. It tells you that the groupings matter, the feature groupings matter. Think about that in your model design so that you don't run into problems. Because if you're picking feature importances, your model may decide that, well, Constitution 27 and Constitution 7 explain all the variants in the model. Well, that's problematic because there's a lot of signal elsewhere. But I am going to basically ignore all of that tonight because it's your job to do your homework and figure this out to build a good model. I'm just going to give you a framework so that you can iterate faster. You should be aware of these things. That's why I'm going through it tonight. Let's take a look at the eras and split them on the median value of eras. There are other ways to split the data. This is just how the author of the notebook that I borrowed this code from. Notice I said borrowed because it was open source. But we're going to split it on the median value of the eras. So basically 1 through 60, 61 through 120. We're going to get the correlation for the DF1 data frame. And we're going to compare it. Okay, so correlation 1 and 2. And what we're going to look at here is the difference in the correlations for the eras. What it's going to show is that these relationships are not constant through time. Because remember, there are eras. And so if you look at era splits, you'll see that the data changes. All right, so we're going to run this one next, and then you'll be able to see that you get a different correlation score depending on which section of the eras you slice on. All right, Twitch fam, you're pretty quiet. I've got to have some questions by now. And you know what? I'm going to let you think about those questions while I run a very annoying advertisement. How about that? The YouTube fan doesn't have to deal with this. All right, that section of code finished. Just a couple more seconds on the advertisement. Okay, welcome back. So the code has finished, and now we can compare the correlations through time. So let's run this section of code, and what we're looking at is the difference between correlation in the different periods. Okay, so if you look at the difference in correlation, you'll see that depending on the time period, these correlations are not constant. So that's why we have to treat the data with respect when it comes to the era groupings. We don't want to train a model on all of the eras without doing something about it, because then your model may assume that all the relationships hold through time, and they don't. That's the purpose of looking at this. Okay, so thank you, Base Real, for talking about how you're not sure how high correlation can lead to overfitting. Because if your model determines that a feature grouping or some combination of features explains the relationship in the data, that may be true for a small segment of time, but not for the entire data set. And so it will learn that this feature grouping explains it's everything. It makes the most sense. And so I'm talking as if I'm a model, which clearly I'm not. But, and that actually has a double meaning. I'm neither a fashion model, nor am I a machine learning model, but I'm paraphrasing, if you will. This model could potentially say that this feature grouping is important, but is only true for 2 or 3 eras. That could be really bad. Thomas Mott says, what techniques do you use to reduce correlation? L1 or L2 regular, I can't say that. Regularization. Yes. Yeah, you can certainly do that. Also, later on, I'll show you a way to not even deal with that. We're gonna split the data into subsets, but you'll see. Okay, so now we've seen that the eras are important and it changes the correlation for the feature groupings. Let's take a look at these feature scores, though. All right, we're going to run that. And then you can see how each column scores by itself. So we take a column and see how it scores on its correlation individually. And you can see that some have negative correlation, some have positive. For instance, strength 34 seems to have the highest correlation in terms of its own performance, if you will, if it were itself a prediction. You can see it is informative, at least. Okay, so let's see here. That holds true after I run that code. But single features do not work consistently. This is a note from the other notebook. So here we're going to create a variable by era correlation. All right, and so what are we doing? We're creating a pandas series on era, which is the NumPy correlation coefficient on the TDF variable we used earlier on the target. And then we're going to look at feature strength 34 by itself, because that was the one that was strong earlier. Right? We're going to constrain it to 0 to 1. And then we're going to plot its performance on era. So this is pretty important because you can see how this performance changes over time. Sometimes it's as high as over 8% correlation by itself in the early time period, but it actually flips negative. Here is why this is a problem. We are scored and paid on our positive correlation, which is what the hedge fund uses to trade on in the actual stock market. So if you have a positive correlation, it means you're going to get paid. If you have negative correlation, you're going to lose money. Generally speaking, in the in-sample at least, in-sample performance of that feature column is above 0. But anytime it's below 0, you're going to lose money. I don't know about you, but I don't like losing money. So when I see this, I have to do something about that because I want it to be over 0 as much as possible. The point, though, is to be mindful that the correlation changes over time. It isn't always consistently performant. So what about the rolling 10 era average? Maybe there's some trends to see here. So let's look at that. And you can. So on a rolling 10, this particular feature is really strong early in the data set, and then it falls off, loses performance at some point in the middle, and then it picks up steam again. Well, that's fairly familiar. Wasn't there a plot earlier when I looked at the number of rows per era? It seems to be related in here. There must be some interesting feature of the data in the middle of the data set. I'm not suggesting that that's true. I'm just using my eyeballs and saying that there's something similar going on. I would just say, take a look at it yourself. So let's split this up again. Let's take the train, let's split it into the median, so 1 through 60, 61 through 120. Put it in DF1 and DF2. And now let's train some models on it. So now let's actually do some regressions. Okay? So we need to import sklearn. From sklearn, import linear underscore model. Let's do that. we're also going to fit it on the features and target for these splits. So we're creating a model on the first half of the training areas and a model on the second half of the training areas. Okay, that lets us know that we're fit. Now let's take that performance on both. So we're going to take the score on the DF1 and DF2 and for each model, and we're going to get the R squared. So the score is just the in-sample performance. Again, in-sample performance doesn't really help us. It's not that informative, but it will show you at least the difference. So if we trained it on the first one, it gives us the out-of-sample for the other. Okay, so we trained it on one, evaluate on one. It shows the in-sample is pretty good, but how does evaluate on one work for that model? Well, it's not nearly as good. So the in-sample is misleading. So, well, I'm sorry, if you train on one, evaluate on two, it actually turns out negative correlation, or negative R squared, sorry. So it doesn't explain hardly anything. And then train on two, right, it looks like it's better, but the in-sample on the first half is very poor. These models are no good. And again, it's because the in-sample performance may look good, but its out-of-sample performance may not be very good at all. So let's take a look at this one. Here what we're doing is we're looking at how train on one, evaluate on one, when we look at predicting DFX, the features. So we want to see, what does this model look like when we take the correlations? So now it's not R squared, we're looking at the correlations. So again, train on one, correlation is 6.5%. That seems pretty good. But look at the out of sample, it's only 3%. So here we train on two, in samples 5.8, out of samples about 3.5. So it's a reduction. And that's just on the training data. So again, we have to be cautious with in-sample metrics. They are not helpful with this particular tournament. Now this, I included this. I don't think it's necessary to run this on. I don't intend on doing it. But you can train a standard logistic regression as a classifier. So if we treat the target, multiply it by 4, and take it as an integer, okay, that gives us whole numbers to use. And we can fit a logistic regression in that way. Now, this took a little while to run. That's why I'm not going to do that. Okay. But we can look at how it performs for the first and last classes. So the zeros and the ones. You can see on zeros and ones, the performance is pretty good. But the middle has some issues. All right, so we're able to plot that. Zeros and fours, zeros and fours. You can see it in the corners, right? So very interesting. I don't do anything with that in my prediction models. I leave that alone. I believe that the author of that notebook was just pointing out that there's some information there in case you're able to do something with it. I don't teach my students to do this, but I share it with you because they wrote the notebook. The in-sample correlation is 5.4%. So let's take a look at that. Again, I'm not going to run it. The Numerai score on that is pretty strong, but a standard linear model actually does better. Okay, and that's what this shows. So we look at a linear model fit on all the train data. We score it, take predictions, and then get the Numerai scores. This one I can run. It shouldn't take too long, so I'm going to go ahead and let it run. But we define the model as linear equals linear underscore model dot linear regression. We fit linear on the training data, which we've pre-selected just the features. And then we have also the target from the train set. We can score it and then create predictions. So we're going to predict on in-sample DF train features. This gives us a prediction set that we can turn into the Numerai score function. It needs to be past our predictions and the actual known value of the target. And in this case, we get 5.4% compared to roughly 5.3%. So a regression model still does slightly better. Now, we should talk about cross-validation strategies. I used group K-fold in a previous notebook, and I continue to think that that's the appropriate one. There are many others. Okay, so here we have 4 potential ones. K-fold with 5 splits, K-fold with 5 splits, and shuffling of the eras. Actually, in this case, is not even looking at the eras. And group K-fold with 5 groups, and time series splits on 5. So let's just store this. And again, we have the correlation score. I think this is where we transition to the other notebook. And we also have some metrics. So for the cross-validation iterator, we want to print which one it is. And we want to get the mean of the cross-validation score on linear regression with a single job. CV defines our cross-validation strategy. If there's a group call, we're going to give it to it as eras. This is important for the group K-fold. In the metrics, we're making a score called correlation score. And greater is better. Yes, of course, we want greater is better because the higher the correlation, the more we get paid. So that's what we want. I'm going to go ahead and run this. I think it takes a bit of time to run. So this is a great chance to get some questions. So how are we doing, Twitch fam? Everybody keeping up? Anybody trying to run this locally? I'm curious to see if anybody's running it on their computer. So the link to this notebook, let me pull that up for you. It's in, I do have it in chat. I don't know if you're able to scroll up, but let me just copy it for you. There you go, Thomas Motz. Thankfully, this is linear regression. Linear regression runs pretty fast. And so it just finished K-fold. Now it's going to do the other one. Hey, no worries, Thomas. You don't have to run the notebook since you're pretty far behind as it is. You can just scroll down. The outputs will all be the same. That way you can see the same thing I am. I'm running the code for you. So just know that it works. If you do still want to go ahead and run it, just click open in Colab. Open in Colab, and then you can run it. And of course, all this should port over to your local machine if you want to run it locally. Thomas Mons, do you think the time series is causal? So is training on later eras going to create a data leak for earlier eras? That's suspected that is true. I don't necessarily buy it because everything is neutralized across time. Although I had this discussion with one of the team members recently, and he said that there may be relationships among the columns that don't even occur until later in the time set. And so if that's true and you train on a later era before an earlier one, then the model may try to pick up on that. And if given similar data to what's going on early in the era sets, then it will assume that relationship exists when it doesn't. I don't think it matters. I'm not willing to change my production models to prevent that, but it could exist. And so since you're asking that question, I assume you have the skill set to deal with that, and I would encourage you to try because it certainly won't hurt. Any other questions? And again, we're just waiting on this to run. Also, I'm going to give you a fair warning. I got to run another commercial break in a couple of minutes. That way I don't have pre-roll ads. For the K-fold cross-validation, does the model that performs the best on a particular fold get selected, or are they all representative of the same model's performance? It depends on how you accept it. So I would just refer to the sklearn documentation. But in this case, we are trying to find the parameter set that performs the best. And so when we call the best model, it's only going to give us the one that performed the best on whichever subset that was. So your mileage may vary. I'm going to show you later on in the stream how to kind of correct for that. So I think there's an ensemble approach that we can use that's very simple to implement, and that's what I have my students do. But you can see how the performance differs depending on how you select it. In this case, it looks like K-fold with shuffles true seems to be the most performant. I find that dubious. I would look at group K-fold personally because I think that's better because it keeps the eras separate, kind of parts it out. And then time series split shows the lowest performance, but in fact, it might actually be better. I don't know how it looks in out of sample. I do not use these in my production models. All right, now, this snippet is just looking at the eras in sets of 10. So that's it. It's just looking at how many rows exist in a group of eras. The final, so this is also interesting because this is 0 through 9, and then this is a single era, the way it was split. So this is probably just a bit of coding error on the author's part. Again, I'm just presenting what was pre-done and kind of walking through it for folks. But let's take a look at those 10 blocks. What are the correlation scores? So we're taking a linear model. We're training it in groups of 10. We're making predictions. And it's running. And then the next step, we'll create the scores for it. Take a look. And while this is running, I'm actually going to do that awful thing, and I'm going to run a quick ad. And YouTubers won't have to deal with this. Okay. Some of you may know, but if you do subscribe, or if you have a Prime subscription, you can actually subscribe to my stream for free. Then you don't have to look at any ads at all. That's pretty cool. All right, so that's finished. Now, how do they perform? So we're looking at groups of 10. So we have a test and a train. So we're training on 0, testing on 10. So if you see the in sample will run in the diagonal, and then the out of sample runs corresponding to that. So not very high correlation scores, right? Again, this is just a simple basic OLS. There are certainly better models out there, and I would encourage you to explore and experiment and find it. But that's what this table shows. It splits it into groups of 10 and then shows you how the correlations look across time. So each row here is the training block of eras. Each column is a testing block of eras. There is a period in the middle that does not seem to be relevant to other eras. The overall performance seemed to decrease a bit over time. Let's take a look at that. So this was the results data frame. So this is the same data, but graphed visually. Okay, and it's showing that the early is good, so dark green is good, light green is not as good. You can see how that transitions through time. Okay, there is more to this notebook, but it's a little too advanced, so I omitted quite a bit. So I'd encourage you, if you want to learn more and explore it, check it out. Hey Joe, you just caught the end of the analysis and tips notebook. Welcome to the stream. Joe is actually now you're a top participant in the tournament. Joe, what rank is your best model? Are you in the top 20? Well, watching in stealth. Well, at least I hope you've hit that follow button. Rank 21, you think you're going to make it to the top 20? You might. 21's pretty good, my friend. Congratulations. So check this out. What we're going to do next, I'm going to post. You were ranked number 4? I don't remember that. Well, good for you. Check this notebook out. So what we're going to do is we're going to partition the training data into subsets. And we're going to explore the parameter space to tune a model on that subset. And then we're going to ensemble these subsets together and create a meta model that is better than any one of its individual parts. I think it's easier just to do it. So let's do it. Click that link. And then click Open in Colab. And then you'll see this notebook. Now again, you're going to see in the settings, I have it in dark mode. You can switch it how you like. So light or dark. I prefer dark. And then I'll walk you through what we have going on. If you could, just let me know when somebody has it open so I know that A, the link works, and B, that we're ready to move on. Okay, great, Thomas. Thank you. So yeah, you're just going to hit Open in Colab. And then I'm going to walk through these lines of code before we run it. All right, so I assume that you have this view. There's some things I need to talk about. So if you want to install things in your Colab environment that are not pre-installed, you can do so. You can pip install. There's a shortcut for that. Use the exclamation point and then type pip install, and you can install an external package. In this case, we want Numerai. Numerai is a community-written API interactive tool to download the Numerai data. It also has convenience functions for using the data. And it allows you to programmatically upload your prediction set to the hedge fund yourself. And we'll get to that at the end of the notebook in the next step after this. But this is how you would install something external, which you can then import. And your standard import statements are as follows. Import pandas as PD. We want sklearn. We want to get model selection. We want linear model for this particular notebook. You may use anything you want if you're tuning the hyperparameters. So, Joe, the difference is that Numerai is written on top of Numerai API. So it's like 3 layers deep in terms of dependencies. Most people that have been around a long time have just used Numerai. Certainly check it out. In fact, I should look at the GitHub link for that. If you'll stand by a second, I'll try to do that. I can't remember if Numerai hosts it now or not. I think they do. Yeah, so here, I'm going to post this for you. So that's Numerai. For reference, Anson Slyfox in RocketChat, he is the, gosh, I forget his title. I think he's chief engineer, president of engineering, something like that. Apologies, Anson, I forget your title. Shame on me. But he actually advises people to migrate away from Numerai and toward Numerai API. I'm a holdout. I'm going to use this for as long as I can because I don't want to rewrite all my code. I had my students use this as well. So Numerai will download the data and load it in a convenient way. It also automatically switches it to float 32, so it takes a little less RAM, but it still has some memory issues when it downloads the data the first time. So we could go ahead and run this. I've already run it for you. I'm going to walk you through the code so that you can see what it does. We're going to define the data as a variable called data. We're going to use Numerai, which we imported as NX. We're going to download it. But here is what we're doing. I call this notebook partition_1_optimizer for a reason, because this is just the first partition of 4. And I put a comment here so you can see it. I call it X1 train. Okay, X1 train is era 1 through era 30. So that's 1/4 of the total data set. And I give you the numbers too, because my students seem to have problems with that, shockingly. But that way you can switch in and out. What we're doing is we're fitting a model on 1 through 30, and we're using 4 splits of that for a group K fold. If you wanted to change any of it, literally just write over it. So we can go 31 to 60, right? So that would be the second partition of the data, right? For this example, I'm only going to do it on the 1, okay? Also, you could split this 3 ways. You could do it twice. I would recommend at least 3, though. Give the data a chance to be different and for the model to find a better parameter space. You know what? Let's just run this. Why not? So here's what's happening. My Colab environment already had all of this. So it says that it doesn't need to upgrade or do any of that. All it needs to do is download the data. So since I've already done it once, I get this really long, ugly string printing going on. But you can see it's still pretty fast. It's not that bad. So it's just going to download the data, and then it's going to open and load the data and follow the pre-written script that I did. All right, 22 seconds to download the data set. Now it's unpacking it. You should see a RAM spike up here as it loads the data in, because it was a zip file. It has to unzip it, convert it, and do all its backend stuff that's going on. Numerai does this automatically. We're just waiting on it to load. So this is what I advocate to my students. Split the data up into parts, train individual models on each partition, and save the best settings as you go. So we would tune the hyperparameters for 1 through 30. We would save those hyperparameters, and then we would do it again on the second partition. How would we change it to the second partition? We would change the era numbers. Or you could clone this notebook and have the second notebook correspond to the second partition. That's up to you, right? That's how you want to run your notebook. None of my business. I personally like to have it all in one notebook because I can't stand having all those tabs open. Even though I have a gajillion tabs open all the time, I'm a total hypocrite. Do as I say, not as I do. So that's what we're doing. And this will make more sense when we move to the... Oh, see, I crashed it. See, check that out, Joe. That's what happens. So I crashed it because I used all the RAM. Numerai is just lovely for that. I don't need to run in a higher RAM setting. I just need this one to run. It should have worked because I had it run just a second ago. I'm going to run it again. Let me know if anybody else breaks it, because sometimes it'll pop up and it'll offer you to run in a different runtime that has more RAM. So what does this one have? This one's giving me 12 gigs of RAM. I should be able to go to a higher runtime type. So if I switch to GPU, I wonder if I'm going to get better RAM. Let's try that. Nope, that's the same. But now I have GPU access. So GPU access is great if you're going to run XGBoost. Cream Mongoose. I just think that username is awesome. How would you purge a few errors between train and validation splits to limit data leakage between train and validation eras? Yeah, I'm not worried about purging there, Joe. I don't care about that at all. But you'll see, this will make sense because I'm considering that a model will only see 30 eras at a time. And in that sense, it's isolated from earlier time periods and later time periods. See, I think you two, being Cream Mongoose and Thomas Motts, I think you two are more advanced than you're letting on. And while I appreciate you hanging out with me, I am not willing to scare off my target audience, which is newcomers. I think we should save these conversations for when we get into the more advanced stuff. But I appreciate the discussion nonetheless. Did that one run this time? I think it did. So that actually downloaded in 5 seconds. We didn't overwhelm the model. But this next piece is pretty important. So I chose what I already know to be a pretty terrible model. Okay, so I would not advocate that you use this in production. But I am choosing it because we can look at the parameter space that we can optimize. So Cream Mongoose was my handle given to me in the Quantopian contest. Really? I want to know what algorithm they use to come up with these fake usernames. Because that's just very different. Like a cream-colored mongoose? I don't know. It's very strange. Whatever. Hilarious. Color plus an animal? Hey, I don't know. It's funny actually. My Google Play username is Fierce Professor. And I got that well before I decided to get my PhD. So maybe all this time Google was forcing me to be a professor so that I could use Colab and teach it to people. I don't know. It's a conspiracy. Oh, by the way, I got to hit y'all with an ad. I know I'm not keen on it, but it prevents people from joining and having to watch one straight out of the gate. Also, if you subscribe, you don't have to have an ad. All right, so what I wanted to show here was ElasticNet. Not a very good model in production. I do not recommend it. You get pretty horrendous live scores. But for the sake of hyperparameter searching, it's decent because it's really fast to run and you can see the results. So we're going to use ElasticNet. Now, how do we know what parameters can be optimized? Well, let me just drag this over because this is from the sklearn website. So let me post this link in chat so you can follow along. So you click this link and you'll see in this top piece where it says class. Okay, everything through here, this is the default settings of the model. So if you just put ElasticNet open and close parentheses with nothing in the middle, all of this stuff would represent the default settings. All the stuff in here also defines what we can search for. So alpha is a term that we can look for the best setting. And also tol, or tolerance, we can try to find the best tolerance for the model to fit with. So let's do that. Okay, those are the two we're going to do. So what we do is we would copy over those default settings and then delete out alpha and tol from the interior of the parentheses. And then we create a params1 dictionary in Python, and we tell grid search which values of alpha to search across and which values of tall to search across. In this case, it's going to look for every combination of these two and find the best. So let's run that. I pre-wrote this for you so that you don't have to worry about writing the code to make your life just a little bit easier. But for any model, you would just look for which ones you want to optimize, and you can just change it in this parameter space. That's what I had my undergraduate students do when they were developing their models. It helps to have somebody write it for you. Also, like I said, Elastic Net's really fast, so it's already finished. That's nice, because I think that speed matters when it comes to live coding demos. So that finished really quick. What's our best setting? So if you do gs1.best_estimator, it spits it out. It tells us an alpha of 0.001 with a tall of 0.1 gives us the best settings. So here is what you do. Copy this as a note to yourself. Partition 1 settings. Right? And that's really it. Just comment it out so that if you click run all, you won't run into it. Now what you've done is you've found the best settings for this model on the first partition, which would be 1 through 30. Now that we have that, we can go up to the top. We can change this to 31 through 60 for each of these parts and do it again. I'll save you the trouble because I've done this a few times now. The parameters are the same for linear models across the different partitions. But you would do that through each one of these for 1 through 30, 31 through 60, 61 through 90, and 91 to 120, just to make sure that the parameter settings that you've identified are the best truly are the best. And save them. Save them for yourself to help you to not have to write too much code. Because here's the next step. So what we're going to do, let me just find the link because I keep clicking around. I got to find it. The next part is the actual production model. And I, of course, wrote that for you. This is the same thing that I give my students. Okay. Here, I'm going to put it in Twitch chat. Okay, so go ahead and open that link. This is your production model. Let me reconnect my runtime. This should look somewhat familiar. Assuming that you found the parameter settings for each of the partitions, we're just going to define those training partitions in this first cell. So there's 4 partitions. There's 4 X train, 4 Y trains. But go ahead, open the link, click open in Colab so you can follow along. I'll wait just a second while you get that set up. All right, so I just assume that people have had enough time to open this up and get going. Again, we need to install Numerai. That will run very fast. We're going to import pandas and NumPy, and also we're going to import linear model from sklearn. Whichever model you use, you're going to need to make sure you have your dependencies sorted out, okay? In this case, we have partition 1, which is 1 through 30, 2, which is 31 through 60, 3, 61 through 90, and 4, 91 through 120. So we have 4 different subsets of eras, all using the same model. Okay, and we also need to have the corresponding dependent variable, which we have here. Let's go ahead and run this. It'll go fairly quick. Let's hope I don't crash the runtime this time. You only see this funky printout if you've already run this cell, and it's basically each step printing a new line. It won't do that the first time you do it. All right, so that's moving along. We're still waiting on the cell to process. I can at least talk about this next cell. So we need to define the model 4 times because we're going to have 4 models on 4 different partitions of the data. So I switched it from ElasticNet to linear regression just for speed's sake. Also, it's better than ElasticNet. ElasticNet is atrocious in its performance, so I wanted to show you something simple that you can replicate yourself. But in this case, you would copy over your settings from partition 1. So here we have ElasticNet, right? You would copy it over, and you would put it in your L1 line here. You would overwrite this, and you would have it say ElasticNet. Take the comments out so that it's all in one line, so that you have ElasticNet 4 times, or whichever you have. Maybe it's 4 different models. 1 model by itself per partition. What if you did an ensemble where you had 3 models per partition 4 times? That, I don't know, that could be performant. You can be very creative here. You can slice it on feature columns as well. All of these are valid, and they could be performant. I will just tell you that one of my students took this basic framework and created a top 50 model, and he was in the top 50 for weeks. Weeks. So I know that this method works, and I'm quite comfortable sharing it with people because it is performant. But you really must do your own homework. You have to experiment with different models, and you got to find something that you believe in. Because if you don't believe in it, you won't stake on it. And that's the ultimate goal here, is to stake on a model that you believe in. It signals confidence in your model and your predictive abilities, and you'll get paid on it. That bottom line, that's why we're here. We all want to make money. Beyond learning how to code and participating in the most difficult machine learning tournament in the world, we also want to be good at it, and you can be. All right, so it looks like that ran. Let's store those models in L1, L2, L3, and L4. And all that is just ways of writing and remembering what's what. So we then need to fit the model on X1, X2, X3, X4, and so forth. And then also just use the convenience score, correlation score. We're not too worried about rank at this point because we're not even sure we're going to put it in production. I'll show you whether we should or not. So that fits really fast. That's why I use linear regression. We need to build predictions. So here now, this is finally where we're using the validation data. We're finally checking out of sample. Each model is being predicted on. We're predicting the validation data per subset of training data. Okay, and we're going to store it in its own variable. Let's do that. That goes really fast because it's a linear model. And we want to get the scores. We're going to take the correlation score of the known validation score, or the known target, against the prediction. So we're figuring out of sample what's this going to look like. So we're going to store it in these variables, and then we're going to print the scores. You see, I've already done that, but you'll notice that the L1 is the most performant, followed by L2, and then it drops off from there. They're not super great, but at least they're not negative. So that's interesting, isn't it? But what happens if we combine all of these and average them together? In an ensemble, generally speaking, an ensemble is better than any one of these models by itself. That's what I have my students do. So here I build a convenience function for you. I'm going to create a new data frame that stores all of these predictions together and comes up with a new column called average predictions. And the way we do that is we take the predictions from the first model, which here is preds.l1 preds. We add them all together and divide by 4. We just take the arithmetic average of each model's out of sample predictions. Let's do that. All right, so that's stored. How do they do? What's the average out of sample score? It should be higher than any one model's individual score. That's what we're going to look at. And you can see that, in fact, it is. So when you average across, you get a score that is higher than any one model by itself. That's very important. That's the strength of ensembling. So Thomas Motz has a question, just trying to follow. L4 underscore score is trained on the last set of eras, and the 0078 is the score on out of sample, e.g. the first 3 sets of eras. No, actually, Thomas, the L4 score is on the validation data. So we're looking at the score on validation because we're predicting on X test. And so above, you'll see I define X test on the validation data. So this is truly out of sample. This does not come from the training data at all. This is wholly out of sample. Up to this point in the Twitch tutorials, we have never looked at the validation data. So this is our first chance to see how our models have done since we started out. It's a great question. I'm glad you asked, because if that wasn't clear, I want to make it clear now. But you can see how X test was defined as the validation data. Each of the models predicted the validation data. And we print that correlation score, and you can see that they do generally kind of boring. But when we average them together, they do a lot better. So the average of all of them improves above any one single model's prediction. That's the power of ensembling. That is something that I encourage all of my students to do, and I would encourage all of you to do as well. In general, an ensemble is better than any one model by itself. This is just linear OLS. This is the most basic regression model that we can even use. I wouldn't stake on this. Okay? I wouldn't stake on this. I'd be very curious, though, if somebody wanted to, if they had a free slot in their tournament account, if they were willing to upload this and see how it does on the live data. I don't suspect that it would be super awesome, but I also don't suspect that it would be so terrible that it should never be used. I'm just curious how it would do. In the cell below, I create a CSV file. This is how you will submit to the hedge fund. This is it. You've done it. If you followed along all this time, you've come full circle. You went from merely being introduced to machine learning, and now you have a framework to develop a production model. So, yeah, try it out. I make no promises that you'll make money on it, but again, one of my students used this, and they were able to get in the top 50 for weeks. So I know that it's performant. But here, I want to be clear on this because I couldn't believe it. Some of my students just really didn't, I guess they didn't read the notebook. But where it says username, trade this out for like your actual username. Like, it's not username. I thought that was easy enough. Apparently it wasn't. I digress. In fact, it's not even necessary, but it just helps you to find your file in your computer. Okay? But we need to know the tournament name. This is done. Don't change it. I put a comment here. Don't change it. And I create all these other functions so that at the end, it spits out a CSV file that you can use to submit. Okay? The final column is called prediction name. That's important. Because when we create this CSV file, that's what you're going to submit to the hedge fund. These are your predictions. This is literally predicting the stock market every week. Also, if you delete these comments and create an API key on the Numerai page, just put in your public ID here and your secret key here. And then what you can do is you go into runtime, run all, and do this on Sunday. If you do this every Sunday, your predictions will upload for you automatically. Hands off. You're done. It's almost like having compute. The only glitch is that you have to be near a computer and you have to do this every week. But guess what? If you open Chrome on your phone and you open in desktop mode, you can open this and do it in your cell phone because all the code is being executed on Google servers. So you don't even have to use a computer for this. You use a computer just to initially get your model set up and then just click run all in the top in Colab and you're good to go. It's amazing. So you can do this anywhere in the world. It just takes a little upfront work. Now, if you don't set up the API, you'll need to comment this out again. All right. But in the last cell, take the comments out here. This will download to your computer. Okay. So when it downloads to your computer, this is the prediction file that you upload on the Numerai website. That's it. Guess what, Twitch fam? We did it. We went from nothing all the way to a production notebook that creates a prediction file that you can send to the hedge fund. We never peeked at the validation data. So we took a scientific approach. We said, let's find the hyperparameters that works for the partition that we're training on. We created 4 different partitions because we know that the eras are different. We saw that when we explored the data. So we created 4 different models to look at different time frames separately. And then we averaged them all together and created a single model, what we'll call our own meta model, the ensemble, which is individually stronger than any one of them by themselves. And we did that with just the most basic model that I could, which is linear OLS. Thomas Mott says, is this what they call stacking models? This is not stacking. This is just simple. This is actually just a voting regressor. We're just taking, each model has a vote, and that's its prediction. So for instance, let's just use a 1-row example. Model 1 says it's a 0.2. Model 3 says it's a 0.3. Model 4 says it's a 1. And you just average across, and that's the vote. Right? And so it takes the strengths of all the models and kind of blends them together. It's extremely performant. But there are many different ways to do this. Like I said earlier, what if you had a voting regressor for each partition? So if you took 3 different models, trained it on 1 through 30, and averaged across those 3 different models, and then you average across that as well, how good would that do? Could do very well. Also, what if you sliced on partitions, but you also omitted half of the features? You could do that too. And maybe that's performant. It could help to limit overfitting on individual columns. That's for sure. What if you omitted entire feature groupings? What if you just didn't give it charisma in one partition? What if you didn't give it strength? I don't know. I don't know how it would do. But my overall recommendation is to treat this in a scientific way. Have a research design in mind before you even touch the validation data. Only look at the validation data once. Once. Because if you come back and do it again with a little tiny tweak, your statistical power is reduced by 2, a factor of 2. You have to divide your statistical significance in 2 every time you do that. But if you come up with a new hypothesis, you can do this again because it's completely unseen. New models, that's a new chance. Tweaks of the same model is not a new chance. That's bias. You're just overfitting. This is a great chance for questions because I'm just about done. Go on, bring it at me. Bring it at me. Joe's asking, would you need to normalize the predictions for each model before combining them? So when you say normalize, you just mean to make sure that they have the same kind of distribution? And I would say no, because at least with the linear models in sklearn, the predictions are bound to the same. If it potentially gave negative scores or it was out of bounds, like if it went into negative and above 1, then yes, you would need to constrain it to 0 to 1 so that they could be all combined. But I don't believe that's a problem in any of the linear models. You would know pretty quickly, though, because you would have some funky correlation scores when it printed. But I don't think it would hurt, right? So if you coded up your notebook to do that, no matter what the output was, you're totally safe because that won't affect anything. Like I do min max. Yeah, Cream Mongoose says in response to what I was saying for non-linear models, yeah, you probably should do that. I use min max scaling so that it takes it to 0 to 1 no matter what it was. And that way everything's in the same space. Because if you do any averaging or ensembling, then they have to kind of fit the same space. Otherwise, you'll get some really funky results. But I think you would see that when you did your out of sample testing anyway. But remember, only look at the validation once. Once. You only get one shot at that. Oh, and I'm reading the last part of what you said. You say you do it the way I describe it, but you're questioning if it's the right way. So this is in regards to normalizing the predictions for each model. You do it the way that I'm suggesting to do it, but I know that it works because sklearn, the linear models, spit it out in the correct format anyway. But yeah, you should be careful if you're taking it to more advanced models. And just recall, this is like the most basic pre-written code walkthrough that I could possibly give, because I just wanted to kind of make a Twitch tutorial for anyone and everyone. I intend on doing this a little more advanced, and in that case, maybe we can code up some min-max scaling to make sure that it works for any kind of model. I mean, there's all kinds of stuff that can be done. We've barely scratched the surface here. Any other questions? Happy to help. Happy to help. All right, seeing none, I think I'm going to call it a wrap on my first Twitch tutorial series. I want to thank you all for sticking around. I hope you learned something. I'm going to do this again. So if you lost your way or you fell behind, or maybe you just want to hear me go through it again, because I'm sure I'm going to get better at walking people through this as I do it more often, make sure you hit the follow button and be notified when I do this again. On Thursday at 3 p.m. Thursday, 3 p.m. Eastern Standard Time, I'm interviewing a JPL systems engineer. So the Jet Propulsion Laboratory has an employee who is one of the top participants in the Numerai tournament. I'm going to interview him, and we're going to talk about the tournament. We're going to talk about what he does at JPL, and we're going to get to know HB a little bit better. That's Office Hours with Arbitrage. That's a weekly web series that I do. Again, that's Thursday, 3 p.m. Eastern Standard Time. I'm also doing daily scores and chill. That's a new thing I started doing. It's about an hour long every day not every day. Tuesday, Wednesday, Thursday, and Friday, where I just kind of hang out and we talk about the daily scores. Sometimes people hop on and talk with me about what they think is going to happen, and we kind of review the results. Lately, there's been a lot of burns going on. So that's been challenging, but you can't expect to always earn. That's just not a fair thing to ask of the most difficult machine learning tournament in the world. You all are very welcome. Base Reel says, definitely learned something and looking forward to the next videos. Thanks. Well, I'm glad that you learned something and that you're looking forward to it. Just make sure you hit that follow button. I think it's about right there. And if you subscribe, you don't get any ads. So that's nice too. Subscriptions also help me develop more content because, I'm volunteering a lot of time doing these things, and I really appreciate the follows and certainly subscriptions if you have it. If you have a Prime account, you get a free Twitch subscription to subscribe to any channel you want. You might as well pick me. Yay, pick me. So anyway, like I said, that's all I have for tonight. Thank you so much for tuning in. I look forward to seeing you in RocketChat, Twitter, or whatever means of getting in touch with me. I'll be on tomorrow at about 11 a.m. Eastern Standard Time while we wait for the daily scores. Tomorrow is the round resolution, the final result for, round 224, I think? I forget. It always slips my mind, but I think that's what we're on. It's either 223 or 224, and we'll know what our payout's going to be for the week. And, well, that's it. I'll quit filibustering. Have a great night or morning or whatever it is in your part of the world. I appreciate you again. See you next time.